Okay, can you guys hear me? How are we doing? Are there any questions or comments before we get started? I know it's been a couple of weeks before we since last time we had a discussion. So okay, then if there are no comments or questions, I will get started on the lecture. We were talking about the binomial model last time, and so that's where we're going to be. That's the first half of today's lecture is going to be going over the one-period binomial model again. Oh, there was a question. Yeah, so what's the difference between this class and 485? The difference between this class and 485 is for the first part, there's no continuous time in 421. So you get all your continuous time. All the continuous time material is coming in your next course MF2. And so basically what this class 45, what this is a combination of the two courses. So the first half of 45 is the same as the first half of our class, and the second half of 45 is the same as the first half of your next class. For the undergraduate course, we only have one course available, so we're combining the two graduate courses. So here in the beginning, they're the same up until the first midterm, they're the same, and then the undergraduate course becomes in continuous time, and we'll continue on in discrete time. Yeah. Other questions or comments? Okay, so what are we doing here today is the first half of the lecture is going to be the one-period binomial model. So we'll do risk-neutral probabilities. We have not talked about them yet, so they're going to come today. And then the second half of the class is going to become quite different. It'll be about measurement integration theory. And this material we need to move into a multi-period binomial model. Okay, so we will start out with the one-period binomial model. This is just a quick review of what we did a couple of weeks ago. So we have input, we have a bank account, and we have the stock. These are the two inputs we have. And the bank carries, so there is a one period, so there are 2 time points. There's time 0 and time 1. The bank carries an interest rate. So it always starts out being 1, and it goes up to being 1 times 1 plus the interest rate. And the other one, the stock, the big difference between the stock and the bank is that here we only have one value. When you go into the stock, you have 2 possible values. So this is why it's called binomial. So here you have 2 possible values. So you'll start out here with this 0. So that's the stock at time 0, and it'll move into the stock at time 1. So it will go up or it will go down. It'll be some sort of a coin flip. that'll determine what the price is tomorrow. Right? So there's uncertainty here. So the uncertainty in a one period binomial model, model, it comes from a single random variable. So this is this psi. Right, so psi is a random variable, so it goes from a sample space, it goes from say a heads and tail space, and it takes values over here between, it's either going to be U or D. Right, so this here, this is the domain, and this is often denoted by omega, and this here, this is the codomain. So here we have, so all the randomness in the model comes from this single random variable. And so the random variable, when you put a t in there, you're going to get tails, you're going to get d. When you put heads inside psi, you're going to get u. And so what we do is we take S1, this is our stock price at time 1. This is going to be given by the previous value it had times this random variable. So because psi is a random variable, so will S of 1 be. So when we move into a multi-period binomial model, we're going to have lots of these random variables. So for now, for the first hour or so of today's lecture, this is the picture we have. Okay, so the input parameters will be R. So the inputs, this will be R. That's the one we see up in the bank account. And then it'll be U and D. U and D, that's what we see in the stock. And the first order of business is can we just pick any ones we want, or are there any restrictions on it? And as we talked about last time, there is a restriction on them, and to get the restriction, what we do is we merge the two pictures into one. And to be consistent with no arbitrage, this line here has to sit somewhere in between these two legs. So the no arbitrage condition enforces, so again, we start out with the stock price being S0, we have the two legs, and then we need the bank account to sit somewhere in here. So if we want to have no arbitrage, we need U to be bigger than 1 plus R to be bigger than D. And we very often take D to be positive. And if we have D to be positive, we are sure that the stock price at a future date is also going to be positive. So so we have inputs, but we don't have arbitrary inputs. We have inputs that satisfy this condition. So we have 3 input parameters, and they must satisfy these inequalities. But sometimes there's more. So sometimes, or often you see something like R being taken to be 0. And this is not to say that we still have a bank. This is not to say that we got rid of this left side here. We still have a bank account, It's just that the bank account's interest rate is 0, so it stays flat. Instead of going up, it stays flat. So you'll often see that. And another thing you'll often see, in particular in the textbook that we're using, as he really likes to have his examples have that UD is equal to 1. This is often used in our book. These conditions here, they have nothing to do with no arbitrage. It just means that the no arbitrage condition is just these two inequalities, but you will often see these ones here as being taken to 0, or that the product UD is equal to 1. Okay, so we have that. That's model input. What you never see, I should also say that when we have our random variable, you never see this quantity, which is the probability that the random variable is u. You never see this specified. I mean, beyond p being some number between 0 and 1. So the actual value, the actual value of p, this is irrelevant. For derivative pricing. And this can be a little bit confusing, in particular because today we're going to be talking about risk-neutral pricing, and there we'll have probabilities different than the one we have here, and there it matters. In those probabilities we want to create, they matter for derivative pricing, but the actual probability, the probability that psi ends up being u or psi ends up being d, and these two numbers, d are irrelevant. I mean, up to the point, d irrelevant up to p, and therefore also 1 minus p must be numbers strictly between 0 and 1. Okay, so today's topic is risk-neutral probabilities, and risk-neutral probabilities, they play. You'll see them throughout the course. You'll see them throughout the next course. I had been asked to teach computational finance in the spring, and in that course, risk-neutral probabilities will be this will become a complete standard thing to look at. So what I'm saying is that this topic that we're about to introduce, this is quite important. This is something that would be used in all future courses on quantitative finance. They might look different depending on what context you're in, but the meaning of them is always the same. Right, so remember what it is we want to do. We are interested in derivative, for now at least, we're interested in derivative pricing, right? So we take a derivative. So a derivative payoff, this was a function. Right, so this is a function from R to R. There's nothing random about the function, but the payoff, a derivative payoff, so you need a function, and then you take the function and you compose it with the future stock price, and then this is going to be the payoff. So you take a function, then this is the payoff, at time 1. So what we're having is, given that the stock can take two values, the derivative will pay off one of two things. It will either pay off f of S0u or it will pay off f of S0d. And what we're interested in is what to put here. So what's the price? So what's the time 0 price? So that's out here, and this is time 1. What is the time 0 price of receiving the payoff f of S1 at time 1? Right, that's the question we're interested in when it comes to derivative pricing. And so the way that we did this 2 weeks ago is we do replication. So we buy or sell units. We buy and sell units of the bank. We buy and sell units of the stock, such that when we have those number of bank units and those number of stock units, we have a portfolio. And when we look at that portfolio at time 1, what does that pay out? We want it to pay out exactly the same as what the derivative pays out. That's what replication is about, right? So we're going to buy and sell, say, delta 0 units of the stock, of the bank. And so this is the units that we have in the bank. We're looking at what is the value of that position at time 1. Well, we'll have to multiply by 1 plus r here. And then we also have units of the stock. The units in the stock, what are they worth at the end? Well, this will be S1. And we want this thing to match up with the payoff of the derivative. Right, so if you want to price using replication, we have to solve for delta 0 and delta. And keep in mind, S1 can take two values, right? So this is really two equations. This is the same thing, because S1 can take two values. This is the same thing as putting in S0u is equal to f of S0u, and then delta 0, 1 plus r, delta S0d is equal to f of S0d. Right, so these are my two equations I have to solve. If I can solve these two equations, then my portfolio value at time 1 is going to be what's on the left-hand side. Well, by construction is equal to the payoff of the derivative. Then I'll use no arbitrage and say that if I have two things that have the same value at the end, they also must have the same value at the earlier time. Okay, and then the value of the portfolio, the value of the replicating portfolio at time 0. Well, we know we have to buy that many units of the bank, so that will be delta 0 times 1 plus however many of the stock that I need, delta times S0. So then I have the value at time 1 of the portfolio. So I'm going to start writing PF here. The value of the portfolio is equal to the derivative payoff. Then that implies, in this case where we're using no arbitrage, that the value of portfolio at time 0 equals the derivative price. And so that's how we that's our discussion from last time. So you can see, if I want to get every time I get a new, every time I want to price a claim, I got to go back and solve these two equations. So every time, so every payoff f, that was my function to begin with. Every payoff f would require you solving the replicating equation, so let's call it star. So imagine you had to compute, say, put prices. So this is where f of x would be k minus x plus. Imagine you have to compute put prices for k being 1, 2, 3, up to 100. Imagine you had to do that. So there are 100 different puts here, and you have to compute the put prices for each one of them. Now, how would you do it? Well, according to this recipe, the way that you would do this would be to solve these two equations 100 times. Every time you put in a different f, you got a different set of equations, and you don't have to go and solve. So this here is, there got to be a better way. And there is a better way. And this is what risk neutral pricing is about. Okay, before I dive into this, I want to stop and make sure that there are no questions.
What means put prices?
What they are?
What is the attitude named put prices?
Yeah, those are the values that you would have to put out here. Right. That question mark here. Let me switch over so you can see. Right. This is the price of, this is the derivative price at time 0. So if I put in different payouts here, so I could put in, what did we have? We had k being 1, 2, 3, right? So I could do k equal to 1, so then I'll have 1 minus S0u plus. I could have 2 minus S0u plus, and so on. I could have 1 minus, so then S0d plus. I could have 2 minus S0d plus, and so on, right? So I'll have 100 of these diagrams. And for each one of them, I'm interested in figuring out what this question mark is. Right, and this question mark, this is what I get here, right? This here is equal to my question mark. Right, this here is my derivative price at time 0. It's given by that formula here. Right, so to use this formula, I need to know what delta 0 is, and I need to know what delta is. And the way I get these two coefficients is by solving these two equations. But for each function, f, I get a different set of equations that I have to solve. So I have to solve the same two have to solve similar equations over and over and over. I get one set for each function. So here I just have 100 different functions. And if I were to do that, you would have to solve this equation here 100 times. And this will, of course, not be very efficient. And so the question is there a better way to do this? And the answer is yes, there is a better way, and this is does that make sense to you?
Makes sense.
Okay. So the way that I'm going to introduce this risk neutral pricing, I've done this a few times before. So I know this concept of risk neutral pricing, this can be quite confusing. And I put up a note on Canvas called risk neutral pricing, risk neutral measures. And this is a note that Steve Shreve, he wrote years ago, because our students at the time, they were coming back from interviews where the interviewer had asked them, tell me what is a risk neutral probability measure. And some students were having difficulties doing that. Some interviewers were having a hard time understanding what the students meant when they were saying stuff. So I saved the note and I put it up on Canvas for you guys to look at. So I'm going to try to go through this note now, some version of it. It's going to be my perspective on what a risk neutral probability is. So one way to think about it is like in linear algebra, when you have solved, because this is what we're doing. This here is linear algebra. We're solving two equations and two unknowns. This is nothing else than linear algebra. I need to hit the right button. That one. We're solving two equations in two unknowns. This is linear algebra. Okay, so when you do linear algebra, there are many ways to express a solution. You need to have a basis, and the typical basis that one is using in linear algebra will be, it's even called a standard basis, right, where you have zeros in the vector except for one place. Right? So if you have a basis in R2, the first basis element would be like 0, 1, and the next one, or 1, 0, and the next one will be 0, 1. That would be your two basis vectors in R2. So this here, the following is very similar to basis in linear algebra. Right, so for example, in R2, if I take an element x in R2, so that will be something that has two coordinates, I'll be able to write, we can write x as the first coordinate, x1 times a basis, and then take the second coordinate, and you write that times the second basis. Right, these guys here, these are basis vectors. But of course, there's nothing unique about picking 1 and 2 here. You could have picked something else. You could have picked like, I don't know, 1, and then you could have put 3. And you could have put, I don't know, 4 and 1. That would also be basis vectors in R2. You'll also be able to write any element x in terms of linear combinations of these two. But what makes the standard basis so convenient is then you want to find out what the coefficients are. It's quite easy because you just take the element that you're interested in expressing in terms of the vectors, basis vectors, you just take the first coordinate times the first vector, and just take the second coordinate times the second basis element, and so on. So while you can also write x as a times I don't know 1 2 plus b times 2 1, it's harder to get a and b. So you can do it. It is harder to get a and b. And indeed, you would have to solve a linear system of equations to do it. You would have to say that what would you do? You would say that x1 would be a plus 2b. You get that x2 is 2a plus b. Right? Then you solve these for a and b, and this will give you these two coefficients of them. So I'm hoping you have seen something like this. The point being that if you're working with basis elements, the standard, I should say standard here. This is the standard basis vectors. If you're working with the standard basis, it's a lot easier to express the vector in terms of the basis because you just take the various coordinates and multiply them directly onto the basis vectors. Okay, so how does that come out in derivative pricing in quantum finance? So for us, these basis vectors, they have a name. They're called arrow Debra securities. Okay, so let me look at a picture here. So we're going to have an up. So this is also just called AD. So we have AD up, we have AD down. So AD up is something that looks like this. It'll go, should not write dollars here, it'll go up to 1, go down to 0, and 0 and 1. So here you can clearly see the analog with the basis, because this is 0 1 and this is 1 0, this is 0 1, and that's exactly what we have over here. We're also going to need new prices. These are called discounted. They're called discounted prices, and a fancy word for that is that we're going to change the numerator from dollars to bank units. So this sounds fancy, but it's not really that complicated. What you do is you take S tilde, and this is nothing else than just taking S, which is the original stock price. So if you're looking at it at time 0, then this is at time 0. And then you divide by the money market account's value at time 0. You're looking at it at time 1. And then you're going to get S1. So that was the random variable divided by the money market account value at time 1. So this is S1 divided by 1 plus R. And of course, I'll do the same thing for the money market account, but this is going to be a lot easier. Because if I take the money market account's value divided by the money market account value, I'm going to get 1. And likewise, at time 1. Right, so this here shows that this is like this, has 0 interest rate in the discounted price system. And this makes sense. This is what it meant, what this numerator means. Right? We have switched over to measuring everything in units of the bank. So instead of measuring in dollars, I'm measuring in bank units. And there will be no interest rate. So I can look at this price system. Here I have my average world prices. We're going to get back to those in just a second. So if I'm looking at the discounted prices, so now we have discounted. Discounted prices, so we will have, I'm looking at S tilde 0. It can now go up to, what will it go up to? It will go up to, so it'll be S0, so it'll be S1, well, if it's heads, divided by 1 plus R. This would be S0, heads would be U, and then 1 plus R. It'll be S1 and then tails, S0D, 1 plus R. And then in between here, what will I have? I'll have S0 times 1 plus R. And I'll have S0 here because this is equal to S, the stock undiscounted divided by the money market account value at time 0. And we always take this thing to be 1. So this is still this quantity here. This is 1. So this is how our discounted price system looks like. This one was not like this should be. Right, because this is going to be S0 times 1 plus R divided by 1 plus R. So this here is S0. Like the bank account has a constant value, so it should, wherever it starts out being is what it should end up being. So this is my discounted price system. I'll have the stock, and I'll have the discounted bond. Discounted bond will carry the same value from the initial point to the end point. Okay, so now what we want to do is we want to price these two securities, the AD up and the AD down, in this discounted market. So we're going to price AD up and AD down in the discounted market. So you're going to have prices. Okay, what kind of prices should we expect to get here? What should be the value of getting 0 or 1? So this is at time, this is at the end. We're interested in the value here at time 0. What should be the value over here? What should be the value of getting this payoff? You're getting this payoff at time 1. What should the value be at time 0? And the same thing over here. Well, it's a positive payoff, so it seems reasonable that you should have a positive number here. Let's call this number something. Let's call it Q tilde. And let's call this thing for P tilde. It seems reasonable that P tilde and Q tilde should both be positive. Okay, what else seems reasonable? Well, it seems reasonable that the number you're getting should not be bigger than 1. It should not be that p tilde is 2, because at most you can get 1. Over here, at most you can get is 1. So it seems like q tilde should be positive, and it should be less than 1. P tilde likewise. What else seems plausible? Well, if I take and combine the two, like if I take this and I add them up, then what am I going to get? I will get a diagram over here, which is p tilde plus q tilde. And if I look at the payouts of the sum, I'm going to get 1 and 1 here. So then the question is, if I am in a world like this one, what is the value of getting $1 at the end? What is the value of getting $1 at the end? What is that value at time 0? So in other words, what should p tilde and q tilde add up to? What should that be? Well, if you look at the picture we had over here, what is the value of getting, so here we have S0, and there's a dotted line in here that'll take me out to S0. What is the value of getting S0 tomorrow? Well, it's exactly the same value of getting S0 today. I shouldn't say dollars here. I should just say S0 because it's denominated in the bank units. So getting S0 bank units tomorrow is the same as getting S0 bank units today. There's a 0 interest rate in this discounted price system. In other words, you're just as happy with units today as you are with units tomorrow, when there's no randomness affiliated to whether or not you get these units. In other words, p tilde and q tilde should be, what should they be? What should they add up to? That's right, these should sum to 1. These should sum to 1. So you have a 1 here. So now we have numbers. We have numbers that are between 0 and 1, and they add up to 1. So that's why it's called probabilities, right? We have numbers that are between 0 and 1, and when you add them all up, you get 1. That's called a probability. Okay. How do we find them? How do we find them? Price them up. So we're going to set up the replication. We're going to replicate these two payouts. So which one should we start with? Let's do the 80 up first. So we're going to have a 1 and a 0. And then we set up our replicating portfolio. So that will be delta 0. There's no interest. There's no interest in the bank account because the dotted line is flat. So we will get, if we have that many that many units of the dotted security, we will not get any, it won't change over time. The other one, that one is going to be multiplying on to S0U divided by 1 plus R. And then we solve similarly for the S0D divided by 1 plus R. So we have two equations, just as we've had before, right? You have two equations and two unknowns. You can solve this. If I've done it correctly, you should get delta is 1 plus R divided by S0U minus D. And you should get delta 0 is equal to minus and d divided by u minus d. So this was AD up we're dealing with because it's 1 and 0. So AD up, the initial price is the one we called P tilde. We'll put P tilde out here on the left. So we get P tilde, well, it's going to be equal to however many units of the bank we had to buy times its price. Its price was 1 plus however many units of the stock we had to buy times the stock price. And so we'll plug in, take my solutions, minus what would be d over u minus d plus 1 plus r divided by s0 u minus d times u minus d. Did I do that right? No, did not do that right. Have a s0 there. So the s0s you cancel, u minus d, you can see you will combine. You have u minus d in the corner, u minus d, the s0s you cancel. I get 1 plus r minus d. And we need to see that this is a positive number, right? 1 plus r dominates d. That goes all the way back to the very, very first discussions that we had today, that u dominates 1 plus r, which dominates d. So when I move d to the other side, it's positive. So this is a positive number. So in other words, in my diagram, I know this is for my AD out. Here I'll have 1 and here I'll have 0, and I know now what to put. I know what to put over here. What to put here is my P tilde, which is 1 plus r minus d divided by u minus d. And of course I can then move over to AD down. This is 0, 1, this is my Q tilde. But we already know that Q tilde is equal to 1 minus P tilde. So this is 1 minus 1 plus r minus d divided by u minus d. And we can simplify this a little bit. This will be u minus 1 minus r divided by u minus d, which is also going to be positive because we know that u dominates 1 plus r. So now we figured out how to compute these error-diverse securities, what their prices are. And so maybe we should look at a little example on how to do this. A little example. This often appears in our textbook. He picks u to be 2. He picks d to be a half. Right, so this is exactly one of these cases where u times d is 1, and then he picks r to be 25%. This is like a recurrent example in our textbook. And so if you take these numbers, we plug them into the formula. We'll get P tilde. This is 1.25 minus d was a half. divided by the difference, divided by u minus d. This is 1.5. So what do we end up with here? We end up with 0.75 divided by 1.5. This is exactly a half. And then that immediately implies that q tilde, this is 1 minus p tilde, this is also half. These numbers here, I just took them from the textbook. I've seen, this is both good and bad, right? So he likes these numbers, but this is just a warning. So don't expect p tilde to be q tilde in general. This is something that appears to happen a lot in the textbook, but in general it's not true. We will not have that p and q are equal to a half in general. It just happens a lot in the examples in the textbook. Let me try to launch a poll and see how we're doing up to this point.
Professor?
Yes.
I have a quick question.
Yeah.
I'm a little confused by like the q tilde and like why 0 and 1 are being flipped, like in the AD down.
Well, because these are two different things.
Yeah.
Right. So given that we only have two possible values in the future, I cannot put 1 here and 0 down here, because then they would be the same.
Yeah, like I understand that we got it from using like the concept of a basis, but
Yeah.
I was just wondering like conceptually, is the 0 and 1, does it mean anything in terms of like q tilde?
Yeah. So why is this going to make our lives easier? If this is the question, that I agree with. Why on earth is this going to make our lives easier? How is this going to solve this silly question that I put up here? How is this question? How are these AD up and down? How are they going to solve something like this? And so this is what I will do. I will do now. Like there's a reason behind the madness. Like, why is this particular way of doing? Why is this particular way of doing AD securities? How is this going to help us price these derivatives?
Okay.
Yeah, so we have to do that because right now it just seems like, why not put something else here? Why not put 5 and 4? Why these ones? And if I were, for example, to change, AD down to say 2 here, then I'm going to change what Q tilde is.
Okay, yeah, I understand now. It's still going back to the problem of making it easier to solve.
Yes, and so that's what we're going to do now. So why is this going to make our lives easier? And let me show you why this is going to make our lives easier.
Okay, thank you.
So this is going to make our lives a lot easier, because so how does this help us? So it seems like, for those of you that find this concept confusing, hang in there, because this is one of the things that every single student ultimately will be able to appreciate and work with comfortably. It might take a little while, but my document camera is foggy. So how does this help? Well, let's have a look. Let's have an example that we did last time. So this is from last time. We were looking at exactly pricing an option, f of x. We were pricing a call option with strike 5. Right. So remember the time zero price was 1.2. This was from last time. So now let's get this 1.2. This was found solving the replicating equations. That's how we got this 1.2. So now let's see how we can get this 1.2 a little bit easier. What we do is we're looking at the payoff. We're looking at the payoff. This was, trying to remember what the stock was. So we had the stock, I think we had 4, 8, and 2. Yeah, that's how we had it. And then we had the bank was sitting inside here, going up to 5. So now we discount. So this is the bank. Bank is the dotted line, stock is the solid line. So now we discount. And now the dotted line is going to be from 4 to 4. So we have to divide 8 by 1.25. And if I've done that right, it should be 6.4. And the same thing down here, we're dividing 2 by 1.25. We do this as 1.6. So that's the discounted stock. Okay, and then we're looking at the derivative pair. So here it's the call. I'd be interested in putting something there. And the call is going to be 8 minus 5 positive part. This will be a 3. And down here it's 2 minus 5 positive part. So this was minus 3 positive part. That was a 0. So again, if I discount the discounted payoff, discounted payoff, this will be 3 divided by 1.25, and this will be 0 divided by 1.25. Did I do this right? X is 8, 8 minus 5, this is 3, 3 divided, yeah. Okay, so now we have this. This was the picture we had last time, and we know from last time that this question mark out here, this was 1.2. Now the question is, can we do this easier? Can we do this easier? Yeah, we can do this easier now. How can we do it easier? Well, I have at my disposal what P tilde is, and I have at my disposal what Q tilde is. In this particular numerical example, they're both equal to a half. So I know what the price is of this payoff at time 0, and I know what the price of this payoff is at time 0. Both of them are equal to a half. How can I use that information to figure out what the value of this payoff here is at time 0? Equivalently, how can I figure out what the value of this payoff here is at time 0? Well, how many algebra securities should I be buying here? How would I replicate this payoff here using my 2 algebra securities? I can trade in AD up, and I can trade in AD down. How many should I buy? How many of the AD up should I buy to replicate this payoff? How many should I buy of the up? How many should I buy of the down? How did we get this in linear algebra? We did the linear algebra part. How did I find out how many of this vector I need and how many I need of that vector? Well, I looked at the coordinates. So I just take whatever the first coordinate is times the first basis element, whatever the second coordinate is times the second basis element. So if I fast forward a few pages, I have my coordinates out here. I have 3 divided by 1.25. I have 0 divided by, so the last one is easy. So I need to buy exactly of the AD up, I need to buy 3 over 1.25. And I need to buy 0 of the other guy. Because if I do that, if I buy this many of the ADR, what is the payoff going to be of this portfolio part, the first part? Well, I'm going to get 3 times 1 divided by 3 divided by 125 times the payoff of the ADR. And the payoff of ADR, this was 1 and 0. So that matches up this one here. And then I don't buy any of the down ones, so you never pay out anything. So I'm going to get 0 times 0 or 1. So that matches up. And this becomes much easier because then what is the initial price? What is the initial price? Well, it costs a half each, right? So this is a half times 3 divided by 1.25 plus a half times what, 0. Surprise, surprise, 1.2. So it becomes a lot easier to price derivatives if we have if you have these out-of-the-book securities available and we know what their prices are. Right, so another more general example is so if you take a function, so what are we interested in? We're interested in is f of S0u, f of S0d. We're interested in pricing. We're interested in pricing this this payoff. Payoff comes at time one, and we're interested in figuring out what is the price at time 0 of getting this payoff. Well, okay, we switch to the discounted market. That's easy. We divide by the money market account. Right, this one here doesn't change because the money market account's initial value is 1. Right, so here we should be dividing by S00, but this is already just equal to the question mark, because this thing here is equal to 1. Like what we have here, this is S01, this is equal to 1 plus R times S00. Otherwise, this is 01. Right, so we were interested in pricing the payoff f of the payoff f composed with S1. Currently, we can be interested in pricing the payoff where we denominate everything in terms of the money market account. And how do we do it? Well, the way to do it is to buy how many units of a 81 we want to do. 80 up, we're going to be buying however many units of 80 down. When we want to go up, this is where we get a 1 and a 0. How many 1s do we need to get? We need to get this ratio. This is f of S0u divided by 1 plus R. The up units do not pay anything out in the down state, so we don't get anything. We don't get any payments of the second part of the portfolio in the up state. So in the second case, how many units do we need of the down? Well, we need f of S0d divided by 1 plus R. This is, and so what's the price? This is the price at time 0. Well, how much does 180 up cost? And this is P tilde times f of S0u divided by 1 plus R. And this is the price of 180 up plus, and then we have Q tilde. This is the price of 180 down. F of S0d divided by 1 plus R. This is the pricing formula for a general payoff. And then we can write this here, more compactly. We can write this here as an expectation under this, under these tilde probabilities of 1 of f of S1 divided by 1 plus R. This is where we use the P tilde and Q tilde, the numbers strictly between 0 and 1, and the add up to 1. That allows me to write this sum here as an expectation under a probability measure of a random payoff. And so you take the payoff of the derivative and you divide it by the bank account. It's value at time 1. And this is the risk neutral pricing formula. Are there any questions or comments to that slide? So it's been said, I think some of you mentioned this last time, that this payoff, it should be an expectation of sorts. But it is, but it's an expectation under a funny set of probabilities. It's not P here, and it's not Q here. Right, this quantity Q, this is equal to 1 minus P tilde, but there's no mentioning of P here. And the reason that there is a tilde on top of that E here, and this is because you're computing probabilities not under, not using P, but using this P tilde.
Wait, sorry. So are P tilde and Q tilde not probabilities?
They are.
They are? Okay.
There are many probabilities, right? P tilde can be a half, P tilde can be 0.2. In this level of generality, we haven't said what P tilde is. Up in the example, like that one here, this was my P tilde. And that was a half. But in this example, we have not said anything about what P is. We have not specified P, right? So this is P tilde. P tilde was a half, and we have not specified P's. So remember, P was the probability that psi would be U. But we haven't specified. We have figured out what P tilde is, and we have not specified what this is beyond P being some number between 0 and 1. Maybe I can try to elaborate on this. So there's a difference. So there's a difference. There is a difference. There's a difference between writing the expectation. Excuse me. There's a difference between writing the expectation with this tilde and writing the expectation without the tilde. And these two things are not the same. Right, on one hand, this thing here is equal to, how do we compute an expectation when there are two possible values of S1, right? This here is the same as the expectation of f of, then it's this S0 times psi, 1 plus r. And this thing here is the expectation, no tilde, of f of S0 times psi divided by 1 plus r. Okay, so then how do I compute psi? Here can take two possible values. It can take on the value u. Psi can take the value u, and it can take on the value d. What is the probability that it takes on the value? What is the probability that it takes on the value u under the tilde measure? Well, that's going to be P tilde times f of S0 u divided by 1 plus r plus, and then you can also take on the value Q tilde f of S0 d divided by 1 plus r. And like very similarly, but not quite the same. This here is the same thing as saying now I'm under the P probabilities. This is P times f of S0 U divided by 1 plus R plus Q f of S0 D divided by 1 plus R. This thing here, this is never relevant for us. This here, this is the value of the replicating portfolio at time 0, and this is the derivative price. This is the derivative price. Right. So, yeah, go ahead.
Professor, I have a question.
Yeah.
So I'm having a hard time understanding what's the difference between these two. The E tilde expectation of expectation with a tilde and expectation without tilde. So the probability, I mean, isn't it in the second, like when we don't have a tilde, the probability there as well would be similar to P tilde and Q tilde for Q?
How would you, if I go to the example, yeah, we go to this this example here. How would you tell me what P is?
But isn't it like the sum of P and Q would be 1 always?
Yes.
So even if the second one, I mean,
So here, P plus Q, this is 1, P is between 0 and 1, and Q is between 0 and 1. And the same thing is true over here. P tilde is between 0 and 1, Q tilde is between 0 and 1, and they sum to 1. So that's correct. My point is, when you look at the second part of the paper between my hands, inside here you will find a P. And if you go and look at the example we did, there is no P described here. There is, of course, P tilde described, right? Because that was exactly half.
got it.
So in this example, so you can have P tilde being a half and not know. So this is beyond P being a number between 0 and 1, what P is. Right, so in this example we did, we had exactly this case that P tilde was a half, and we don't know what P is. So consequently, you will not be able to tell me what the right-hand side is because it involves P. Whereas you can tell me what the left-hand side is because it involves P tilde, and P tilde was a half. Does that make sense?
Yes, Prof.
Okay. Any more questions or comments? I would suggest then that we take a little break, and then remember after the second half of today's lecture, remember there's a different Zoom link that you have to click on to get back in there. I'm going to start up that second lecture as soon as we're done here. But let's take like a 10-minute break and get back around 10 o'clock.